Giuseppe, your second lecture. I will be short, so you have more time.
Okay. So thank you, Marcus, and good morning, everybody. Thank you for being here, despite the early time in the morning somehow. Today I will finish hopefully my series of theory lectures, and then you will have a hands-on session with Filippo later this week. But let me just give you a quick recap of what we did yesterday. So essentially, yesterday we saw we introduced variational states. Okay? So as a way to treat larger quantum systems using an approximate, if you want, representation of the many-body wave function that depends now on some parameters W. And explicitly, we wrote this in this way. So now the coefficients of the wave function will depend on these parameters W. And I told you that I classified somehow these variational states into two large families. So the first one, for which you can compute expectation values of operators, so to speak, so compute this expectation value exactly. Okay? Again, exactly meaning with arbitrary, if you want, rounding errors. And two, another family of approaches that we discussed more in detail, which are where you can compute this expectation value essentially statistically. Okay. With some arbitrary accuracy, but not, if you want floating point precision, like in the first case. So you have to increase the number of samples, and the accuracy you have goes like 1 over the square root of the number of samples, as we discussed. And in this specific class, number 2, that we discussed at length yesterday, so you have to satisfy two conditions, A and B. So the first one is that you are able to compute the wave function amplitudes on an arbitrary basis ket k efficiently. And the other condition is that you are able to sample from this Born distribution, okay, efficiently, in or with some mean that is more or less efficient, as we discussed yesterday. So specifically, we discussed a sampling strategy based on Markov chain Monte Carlo and Metropolis, if you want. Okay. That allows you to empirically sample from P of K. There is no guarantee that this sampling is efficient, but in most cases it is. And then I showed you that then computing the expectation value of the operator then reduces to somehow a statistical expectation value over m samples that you've generated from this distribution of an object that we called the local energy, the local estimator of the quantity O. Okay? This was defined yesterday. I'm not going again into the details, but this is just to give you a recap. Okay?
There seems to be one question by Amtu.
Okay.
Yeah, it seems like a proper moment to ask this question, and I actually didn't get what is the big advantage of the second method or the first one that excuses its approximate nature. I mean, how come that we cannot just always resort to the first method because it's exact and apparently quite fast? So what is one big
yes, so let me answer your question quickly. Yes, so the issue is that I mentioned that yesterday, well, maybe too fast. So if you want to satisfy this exact nature here, essentially you need that your ansatz is strongly local, for example, tensor networks in 1D, or they have some strong properties in the parameterization, if you want, of the wave function, okay? So if you want to go beyond these properties, so typically because you want to accommodate states with volume law entanglement, typically, but not only, then you essentially break the ability to compute expectation values exactly. So that's why you have to introduce this larger class. Okay,
Mhm.
but this
Okay.
class 2 contains, if you want, class 1. So this is a broader class. Okay.
Okay. Thank
So
you.
this
Thank
is
you.
the main motivation, I would say. Okay, and then I mean, in order to start answering this kind of question, we wanted to start parameterizing things, and that's where we introduced the neural networks. And in general, I mean, the machine learning ideas from machine learning, where I started doing this yesterday. As I told you, the main goal there is to approximate. You can think of machine learning as a tool to approximate generic, high-dimensional, complicated functions that depend on n variables, for example, right? And the main tool that we discussed that we will be using is, if you want, the machine, right? So in machine learning, you have two ingredients, right? The machine and the learning. So the first ingredient, the machine, that we discussed already yesterday, is essentially a parameterization of this function in terms of what is called a neural network. Okay? So a neural network is nothing but the parameterization. The machine is nothing but the parameterization of this function in this case. I don't know why this keeps happening, but okay, keeps happening. But we discussed the parameterization in terms of what is called a feed-forward network. That again, I'm just writing it as we discussed yesterday. It's a composition of linear and nonlinear transformations, where the linear transformations are given by this matrices W, that those are your variational parameters, if you want, your free parameters. And the nonlinear ones are given by these functions G, that they act component-wise on the entries of these vectors. Okay? So this is what we introduce to be a feed-forward machine, feed-forward network. Okay, so this was the quick recap for yesterday. So when we started discussing the machine, so the thing that we have to discuss today is the learning part, which is also important and will be instrumental for quantum applications. So, so today we start discussing the learning part. Okay. So the learning as in machine learning. So, and in a nutshell, what the learning is to find essentially these weights or these parameters that solve a certain task. Okay. I will give you an example of this in a second, but in general, and this is just for just to clarify the terminology also in the field, there are three flavors of learning tasks that we can do. I will discuss a few. So the one that I will also tell you a little bit more now is called supervised learning. Then there is another one which is called unsupervised learning. And then there's a third one which is called typically reinforcement learning. So these are all, if you want, the different strategies to find these weights that solve a certain problem. And typically, you can also sort them somehow in terms of hardness, computational hardness. And supervised learning is typically the easiest of these three. And then when you go up, the hardness typically increases. But unfortunately, I would argue that the applications that are more relevant for physics are in the harder part of this learning curve. But still, we can manage to do them, as I will tell you in a second. So, but before doing that, let me give you an example of supervised learning. So this easy one, if you want, conceptual easy one. Okay? So supervised learning is at the easy, if you want, end of this diagram because it's easy to explain and to understand. So the idea is that you have a large data set of x's. So x, I remind you that x is a vector of variables, and we have many of these x, as for example for images, right? As we were discussing yesterday. So, for example, you can imagine that I have a large collection of images, exactly as we were discussing for image recognition applications. So I have m images, for example. This is my data set. Okay. And then associated with each of these image, I have what is called, in jargon, a label. Okay. So I have labels. So this means that for each of these image, for example, I have the label that tells me that the first image is, again, imagine that now I have images of numbers, right? And my task is to convert these images into actual numbers. So I have that the label of the first number is 3, the second one is 4, and so on and so on. Okay? So the goal of supervised learning in this case is very easy to write down, the time to understand, because essentially we are looking for a function, f, an unknown function that we typically parameterize with a neural network, such that for each element of this data set, so xi, so this function that will depend parametrically on some weights w, is approximately equal, so as close as possible to my already known outcome, so already known label in this case. Okay? So this is the idea of supervised learning. So essentially it's finding the weights that for all these elements satisfy this equality as close as possible. Okay? So this is very close in spirit to data fitting. You know, it's just a fitting procedure where you find the best ways that satisfy these functional relations. And then the idea is that when you have new images that you haven't seen in the dataset, for example, I write another number 3 that is not in this dataset, this function has already learned essentially from these existing images the structure of how number 3 looks like, and it will be able to predict this label from an image that has never been seen before. Okay? So this is the main idea of supervised. On the other extreme of the curve, we have reinforcement learning. So in this case, you don't have there's no labels. Okay. So in other words, if you want, the main difference is that here there's somebody who has pre-solved this problem on a small collection of instances, for example, these images. But in this case, we don't have, if you want, a pre-solved solution to our problem. So there is only, for example, some score function s of x that we have to try to minimize, for example. Okay, so let me give you an example which is from the early days of reinforcement learning. I think you can see it now. But the typical examples here are in the context of game playing. So one task, for example, in this context is to try to essentially play. Try to play this game in a way that you increase the score. Okay? So you see that here the task, if you want, of this machine is to maximize the score in this game. And what the machine is doing here is that it doesn't have a pre-solved, if you want, strategy to play this game. So where to move this cursor, if you want, on the x-axis. But what it can do is that it can play a lot of games. So this is your data set that you self-generate on the fly. And by playing more and more games, exactly like a human would do, the machine will find the best strategy that is able to maximize this core function. And typically the strategy, as I was also discussing yesterday, is represented by a neural network. Okay? So given these pixels of information, so where the red is, the black, where the ball is, this neural network will give as an output the position, the next position, so essentially the command if you should go on the left or on the right. Okay? So this is the main, I mean, in a nutshell, the idea of how this kind of reinforcement learning approaches work. So they have no labels. So this is the main difference, and that's why they are harder to perform. Now, let's go back, if you want, or forward to the case of quantum physics. That's where we wanted to somehow use these neural network approaches for. But actually, sorry, before going there's something important that we have to discuss, so which is mathematically, how do we describe this learning task? Okay, of course, I forgot to do that. So the learning task, so the learning, if you want, algorithms in general.
There's just one question.
Yes.
By no labels, do you mean that for reinforcement here, we don't feed any learning data set?
Exactly. So there is no learning data set. So for example, in the previous case, the data set is a series of games that you repeat, that you play. Right? So you simulate a game with a given strategy, you find out what is the final score. Then the score will be bad, so you will change your strategy, and then you will play another game. This will be your new data set if you want. But the data set is self-generated, it's not given beforehand, like for the image classification. Okay, is this clear?
Okay, yes.
Okay. Now, so let me tell you a little bit more specifically how these learning algorithms work in general. The main idea is that you have some loss function, so-called loss function, that will depend on these variational parameters, so on these parameters W. So this is what, again, is called in jargon loss function. You can typically write this as 1 over m, the sum over I of some per sample loss. So I will tell you what all these things mean. That depends also on the weights. So again, here I'm mostly thinking about the context in which I have a data set. So I'm thinking about mostly actually supervised and unsupervised learning, not too much about reinforcement learning. So in the context of these two first applications, then it's very natural to write your learning task as the task of minimizing a loss, and a loss that can be written exactly in this form. So let me give you an example. So, for example, in supervised learning, as I was mentioning, the task is to find a function that approximates, right, this yi as close as possible. So you can very nicely define a loss function, in this case, to be, so 1 over m, again, I have m images that I pre-collected, to be the sum of essentially, for example, I can define this to be the square loss. So f of x of y with some parameters w minus my expected result squared. Okay. So you see that this object will be 0, or will have a minimum, only if my machine, my function is predicting exactly on all the elements in the dataset the labels that I have pre-assigned. Okay, so you see that this learning task, again, is just a fitting where you have to minimize this, for example, this quadratic loss. This is only an example. There are many other kind of losses that you can use. Okay, so then what is the main idea? So how do you perform this optimization? So how do you minimize this loss? What people do is that you typically do a gradient descent. Okay. Gradient descent to minimize the loss. So a gradient descent, I mean, as you know, I mean, it starts from computing. So it's an iterative approach. where at each step, so if you want, you have your set of parameters. And then at step, if you want, S plus 1, so now I'm assuming that S is my step index. Okay. My weights, if you want, are taken to be equal to the old values, the values that I had at the previous step, minus, so you follow the direction of the gradient descent, times a constant. So you have the gradient, if you want, so you have the gradient of P with respect to, so this is, for example, the parameter P. Okay, so I imagine that I have a lot of parameters. So W is just a collection of all my parameters. Then I have to do the gradient, the gradient with respect to parameter P of my loss function W. Okay, that depends on W. So this is my strategy in the gradient descent. I will follow the direction, if you want, given by the gradient of the loss. And this multiplicative factor is called in jargon, again in the jargon of machine learning, is called the learning rate. And S, once more, is the step index. Okay. So the learning rate intuitively tells you how fast you are learning, so how fast you are changing your parameters following the direction of the gradient descent. So this is in a nutshell what gradient descent does. And however, there's a twist. So this is not pure gradient descent as you would expect when you learn to optimize functions, which is a very bad technique actually to optimize normal functions. But it's what is called a stochastic gradient descent. Okay. So why it's a stochastic gradient descent? It's called stochastic gradient descent essentially because you can think that the gradient of essentially, if you write down, for example, the derivative of your loss function with respect to your parameter P, okay, because of the structure that we've seen here, okay, so you see that the loss is a sum of losses calculated, each of them computed on one of these samples. Okay. So you can rewrite essentially this gradient also as 1 over m, okay, the sum over I from 1 to m of the gradient of this per sample loss. So you see the difference. So the total loss, I write it calligraphic. The per sample is square L. I hope that this is clear. And then you have the derivative with respect to WP of this per sample loss that depends only on xi. I think depends only on xi, not all the x's. Okay. Now, the main idea, the main interpretation that we can add here is that you can think of this gradient, so the gradient of the total loss, as an estimate of an expectation value. So you see here, I have a very large number, typically, of samples, m. So when this number of samples goes to infinity, okay, you can think that what I'm doing is that actually I'm averaging over a fixed probability distribution given by the data set, this per loss sample. So you see that I'm approximated this, if you want, this average with a finite number of samples that I think are all representative of the same task. Okay, so if I have a finite number of samples, it's like estimated this average. Yes.
There's one question by Satoshi, probably for the slide before. We are taking the gradient of the loss function for just one previous step because the process is Markovian.
Right. I mean, you can see it like that if you want, but I mean, essentially, you can also use information from previous steps. So at this step, I didn't introduce any stochasticity yet. So there's no Markovianity or anything like. This is just the standard gradient descent where you use just the previous step to go down. Yes, you can think it of a sort of Markovian approximation if you want, but there are more, generalized approximations where you take also previous steps. I'm just not discussing them, but they exist. But the main point now coming. So, I mean, looking at this loss function as an average, if you want, over a large number of samples, is that what is happening actually now, due to the fact that I've only taken a finite number of samples and not an infinite number of samples to estimate this loss function, is that typically, so this gradient will be estimated again by this average of the gradient with respect to, I mean, of this per sample loss on a finite number of samples m plus some correction. Okay, so what is the correction? The correction comes from the fact that again, I'm not taking the exact average here. I'm not taking an infinite number of samples. I'm only taking a small population. And the correction, I mean, as you know, is given essentially by Gaussian. So I have that this variable will have as an expectation value, as a mean, if you want, the exact gradient for when m goes to infinity, plus a correction, which will be, if you want, a normal distribution, which will have, I mean, in this case, mean 0, and a variance, which is v over m. So as we discussed also yesterday in the context of Marco chain Monte Carlo, so the variance of the average on the mean of the gradient will be the variance of the mean of the gradient will be proportional to 1 over m, so 1 over the number of samples. So as soon as I send this number of samples to infinity, then this gradient descent, this gradient will have 0 error, if you want. Okay. So there is a question.
Yeah, sorry, I didn't get probably the previous step. When we say the average of the gradient,
yes,
which should be intended to be the distribution over which we average?
Yes. So the distribution we are averaging here on. So when you send m to infinity, okay. So I imagine that you are averaging these over a distribution. Let's call it I of some probability p of xi. Okay, of again the gradient, so the derivative of the loss of the per sample loss. Okay.
Okay, it's basically some frequency or.
Yes. So what I'm saying is that this probability is something you don't know. So
okay.
you only know samples from this probability that are your images, if, for example, okay?
Okay, and the
so
fluctuations
you can imagine that that these images that you have in this data set are uniformly distributing according to this probability P. But
okay.
P is unknown in general. You just know samples. Is this clear? So you can imagine that there is some, very abstract probability distribution of images of numbers that is well defined, but hard to write down analytically, I guess. And you have samples from this distribution. That's my main point. Okay.
Okay, thank you.
So, but since we are estimating essentially expectation values over this distribution, unknown distribution P, using only a finite number of samples, both for the loss function and for its gradient, then it's clear that also the gradient will have will be characterized by the exact, if you want, expectation value when m goes to infinity, plus some fluctuations, so stochastic fluctuations that come from the fact that m, so the population of samples, is not infinite. Okay.
Excuse me.
Yes.
Just a question. Maybe one more draft.
Sorry, who?
No, okay. So it was just what is the V in the variance.
Yes, so V is a parameter. It's the variance, if you want, of the gradient. I'm not explicitly writing what it is. I'm just so let me clarify. So here I'm giving just a hand-waving argument of why this is a stochastic gradient descent. So I'm not aiming at full, if you want, mathematical rigor. I'm just trying to convince you that the reason why this is a stochastic gradient descent is because the gradient that we are using, so this object here, is not if you want, the noiseless gradient that you would have if you would consider an infinite number of samples, but it's an estimate of this gradient with some noise, and this noise is proportional to the number of samples, essentially. So the noise goes like 1 over square root of m, okay, and the variance 1 over m. So this is the main, if you want, hand-waving physicist argument about this process. And the reason why I wanted to introduce this is also because, from a physics point of view, this equation that you can see here essentially is very similar. So this gradient descent equation that you can see here, when the gradient is not known exactly but only approximately with some noise, okay. So this is equivalent, so it's similar to an equation which is known in the physics community as the Langevin equation. Okay? The Langevin equation in the viscous limit. This is so when the mass, if you want, of your particles that act under a stochastic force are zero. Okay, so this is just to clarify. So let me just write the Langevin equation, and then we go back to your question. But as you know, so the Langevin equation is an equation of motion for a particle, again, for example, in a Brownian motion, where you have the standard, if you want, force term. So this is the gradient of, for example, a conservative potential, V. That is the standard force, some plus some F, which is a random force. Okay. So I will tell you in a moment what is more precisely the analogy, but you can already see that you have a gradient of something in this equation plus some noise. And this is exactly the structure that we will have now, because this gradient will have some noise. Then I will tell you exactly how this is done, but there was a question.
Should the noise always have a Gaussian distribution?
All right, so the main simplifying assumption that I'm doing here is that each of these parameters has an independent Gaussian noise. So in the more general setting, you have to consider a covariance matrix among these different parameters, which, if you want, makes the analysis more complicated. But in general, I think that the most general thing is, is to assume just a Gaussian covariance matrix in between all the parameters, which is a generalized Langevin equation. But I wanted to simplify the discussion, assuming that the noise on each direction is independent, which is not the case, but to make an assumption.
Okay.
So then, what is the analogy between these two equations? So you see that in this Langevin equation, the dynamics is a temporal dynamics, because my particles in time are moving under the action of this conservative force plus some random stochastic noise. Okay. So what is the analogy? Because here I don't have any time, if you want, but I have a time step. Okay. So the analogy is precisely, if you want, that so the analogy is that if you want, the time step S somehow corresponds to a discrete version of the time of the physical time t in the Langevin dynamics. And when you go to step S+1, is like going to time t plus delta t, if you want, to some discretized step in time. And then the other important analogy is that in the, if you want, machine learning optimization scenario, my dynamical variables are the weights that are evolving under the action of this stochastic gradient. And in the standard Langevin dynamics, my dynamical variables are the position, if you want, of the particles. Okay, so in this analogy, I have the weights. So I have as many weights as I have particles in the classical Langevin dynamics. Then, if you rewrite the discrete Langevin equation, if you discretize the Langevin equation using a discrete time step delta t, you can show that this is written in this form. So essentially, the position of the particle p at time step t plus delta t is written like the old position minus delta t. So my time step times the gradient with respect to p of my conservative, if you want, potential v of x. Okay, so this is just the standard Newton force, if you want, plus, and this is the important part, a normal distribution, so a Gaussian variable with mean 0, and variance sigma square given by twice the time step times the temperature. Okay. So you know that in this Langevin mechanism, the variance of the noise is by the dissipation, fluctuation dissipation theorem, essentially is given by the temperature of the system. So the larger the temperature in the system, the stronger are the correction to the deterministic Newton, if you want, force. Okay. So, but you see immediately now that we can make a nice analogy, because we know that in the limit in which the time goes to infinity, so in the limit in which, if you want, I run my Markovian Langevin dynamics for an infinite time, we know that the equilibrium distribution, so the probability of observing a certain x, so a certain distribution or a certain positions from my particles, is given by the Boltzmann distribution. So you know that at equilibrium, the equilibrium distribution for my particles will be given by the standard Boltzmann distribution. So that's where, I mean, the analogy. So that's why it's important to introduce this analogy, because we can use then also this probability distribution to analyze the case of the gradient descent for loss functions. Okay, but just to see, so this is the Boltzmann distribution. And then, I mean, if we complete now, finally, our analogy, knowing that the stationary state of the Langevin is just the Boltzmann distribution, we can also compute the stationary state, if you want, for the parameters, right? Again, this is the analogy. So x goes into w for the parameters in my optimization landscape. So to complete the analogy, then I have to associate eta, the learning rate, with delta t. Okay, so you can see it immediately here, because that's what multiplies this gradient. Then I have to also associate the variance that in the first case is given by v over m to this two times the temperature over delta t, and then essentially you can solve for this, and then, I mean, the temperature, so you can identify an effective temperature for the optimization, which is proportional to eta, so the learning rate over the number of samples. Okay? And this means that the probability of observing a certain weight, so in the limit in which, again, the iteration step goes to infinity. So now I'm running my gradient descent for a number of samples that is for a number of steps that is infinite, will be a Boltzmann distribution. In what? In the loss function this time. You see, because you see that here I have the gradient of a conservative potential in the physics case, and here I have the gradient of the loss function. So you see that the loss function plays the role of the conservative force in the classical case, and vice versa. So this means that my equilibrium distribution will be L of W over KB of T. Okay, if you want, this is my T star. Okay, so this means that if I run this simulation, so this gradient, this stochastic gradient descent for long enough, I will be sampling an effective Boltzmann distribution for my loss function. And what I can do is that I can, for example, decrease the learning rate, which is something that people typically do, or increase the number of samples. And this will have the effect of lowering the temperature of the system. And this will allow me also to slowly converge, if you want, to the ground state to the zero temperature, if you want, state of this loss function, which corresponds to the minimum of this loss function. Okay, so the analogy is exactly the following. So we are not doing gradient descent as normally you do, because that will get stuck into a local minimum. Here we are doing a Langevin dynamics, essentially, that converges to the global minimum of this loss function, because we have these fluctuations given by this effective temperature that allow us to escape also local minima, essentially. And the noise is controlled by this learning rate or by the number of samples. Okay, so this is why it's very important. Why we've been very successful to use this, if you want, simple-minded optimization strategy in machine learning. Okay. All right. So now let me go a bit further and finally talk about applications to the quantum case that now at this point are almost trivial because we can introduce a parameterization of the quantum states in terms of neural networks. So that's what we call neural network quantum states. Again, we have a neural network. We know that neural networks are good approximators of high-dimensional complicated functions. So let's use a neural network to approximate the main object we were interested in since the beginning, which is the wave function. Okay? So what we do then is that we want to essentially, so again, I will use now this notation. I will use again, so this is the object that I want to approximate with a high-dimensional function. So just to be specific, again, thinking about spins, these are the amplitudes of my wave function in some computational basis. For example, the eigenstates of sigma z. So I have n quantum numbers again. So k is a collection of n quantum numbers, if you want. And I will want this to be parametrically independent on some weights. And again, very simply now, my parameterization will be of the form of, for example, a feed-forward network. So I will parameterize this object as, again, a feed-forward network that will depend on, that will have some linear and nonlinear transformations as much as I was doing before. So you see that the only difference is not really a difference with respect to the case that I introduced before, where I had, if you want, an f of x. Okay. Here I had an f of x. Now my x in this high-dimensional function is nothing but a given, if you want, ket, so the quantum numbers that appear, in this bra, which is a vector of n plus or minus 1 in this case. So here I have my vector of inputs, which are these quantum numbers that for the case of spins are plus or minus 1, but again, this is just an example that can be generalized to other cases. So, and again, you can see this as a feed-forward network diagram. That we also introduced yesterday, where, for example, you just, so typically what you do is that you plot this again from the left to the right. So your input layer are now my sigma z, if you want, variables that are either plus or minus 1 on each of these sites, if you want, of these qubits, or these sites, if you want. And then, I don't know why. And then you have, again, as many layers as you want in this description. The only constraint, if you want, that you have is that the final layer should have only a single output. So if you want, the only constraint is that the last width, if you want, of this network should be 1, because this is the single output of this network is nothing but the amplitude, again, of the wave function on this given collection of inputs. Okay, and of course, in general, this is complex valued, so this output is a complex number in general. So this is what we introduce in a paper. So it's Carleo and Troyer. You can see more details somehow more details in this paper from 2017. But again, at this point, the idea should be hopefully clear. And we use this neural network to represent the amplitudes of the wave function in a given computational basis. And then we can use, for example, all the technology that we've discussed at the beginning. So, for example, Markov chain sampling, these local observables, to compute expectation values of quantities, physical quantities, over this specific parameterization of the wave function. Okay. Now, just to give you also maybe an idea why we want to use these representations, this question has also popped up somehow many times. So there are some general things that are known. So, for example, there are these general representation theorems.
Just one question before, maybe to be concrete, what is the loss function of your previous example? Is it the energy?
Yes, so I haven't discussed yet the loss function. I'm just discussing now the representation of the wave function in terms of the neural networks. So if you want, I'm just discussing the machine. Okay. So I will finish my discussion on the machine in a second, telling you some properties again of these representations, and then I will introduce the learning part as I did for the standard applications. But the loss function will be defined in a second. But yes, it's the energy, but not only the energy. Okay. I will tell about this in a second. Okay. But so let's discuss first the properties of this machine. So, for example, why this representation can be useful to represent this corner of physical states, right? So this is at the end of the question we want to answer, or try to answer. Well, I mean, there is a very nice theorem motivation, if you want, to this, that comes from the theory of nonlinear functions, because I remind you that these neural networks are highly nonlinear functions. So there's a representation theorem that tells you that if you have a generic wave function, actually this is more general, so let's say general function that happens to be a wave function in this case, but it's not very relevant, of n parameters, then you can always write this function as a composition of two nonlinear functions. So I will tell you in a second what these symbols are and why they are nice. Okay. Okay, so here I'm assuming again that I have n variables. So here, this is a k1 up to kn. You can think again of this as sigma 1 up to sigma n. It's not important. I'm changing a little bit notations, but I hope that it's clear. But the main content of this theorem is that you can write an arbitrary wave function, or an arbitrary function in general, just as a composition of two nonlinear functions, capital phi and small phi. Okay. Actually, it's more than 2. You have n of them for this. So you have n square. So you have 2n square for this small phi, and n 2n for this capital phi. But it's a polynomial number of nonlinear functions, and this is the content of the universal approximation theorem, so-called. That was originally proven in a different context, but very related by Kolmogorov, the actual Kolmogorov, and Arnold, the actual Arnold, in 1956. Okay. And translated, if you want, in the language of neural networks by Sibenko in 1989. So this is highly non-trivial if you think a little bit about it, because it's telling you that as much as you do, for example, when you represent a high-dimensional function with a Fourier series, so where you have a basis of functions and you use these basis functions to represent this an high-dimensional function in terms of these basis functions, the same thing can be generalized to the case in which you don't have strictly a set of basis functions as you do in the case of linear, if you want, representations of high-dimensional functions, but this can be generalized to the case where you have a composition of nonlinear functions. And the main advantage of doing nonlinear compositions is that, in principle, again, in principle, the number of terms in this expansion that you have to take is only polynomial in the sides of the space. So in this case is n. Okay, so it's in the square of n. Whereas if you do the same expansion, for example, this function in a Fourier basis, the number of coefficients that you need in general, okay, is exponential in the number of spins, or in this case of variables. So this is the main difference. But in principle, if you work with nonlinear representations, it exists a compact representation of this function. Is a question?
Yes, maybe I'm missing something here, but I mean, cape psi is already a single nonlinear function, no? So without kind of further properties on this psi function, that's just somehow a circular statement, no, in some sense.
What?
Because I mean, basically just telling me that a nonlinear function k of psi
No, sorry, you're
already a
misunderstanding.
nonlinear function itself.
No, here I'm saying the most general wave function. This is not related to my variational approximation, sorry.
No, it's clear, but I mean, it's already itself a nonlinear function, no? So all that I'm saying is that a nonlinear function is a composition of some other nonlinear functions.
So, but why do you know that the most general wave function is a nonlinear function? I mean,
if I parameterized it, it's a function, or not? And it's clearly not linear, or I mean, it should be, or is this a completely wrong way to think about it? But I mean, if it's defined, it's a function.
no, I mean, the main point is that you can think of this as a generic n-dimensional function of n variables. So you don't know that this is a priori a composition of two nonlinear functions. This is highly non-trivial. Okay? That's why Kolmogorov and Albert proved it. So what you prove is that you can write an arbitrary function as a composition of two nonlinear functions. So this is the statement which is non-trivial. I don't know if this is clear, but
just to add, maybe on the right-hand side you have only it's a summation of a single argument functions. Means it's a structure on the right-hand side which is particular.
Yes, okay. Yes. This structure of the function is extremely particular and it's non-trivial. So this is the result of Kolmogorov and Al.
Okay, yeah, no, that makes sense. Thanks.
No problem. Okay, so this is the first statement. So the first motivation is that, at least in principle, if we are able to find good representations of these functions, phi and capital Phi, we can represent a generic wave function in this form. So this is, if you want, the motivation. And the other motivation is that this family of states, as I was anticipating, satisfies volume law entanglement. property.
Giuseppe,
Yes.
I have a question, if I may. Maybe it's too specific, but are there any properties that these nonlinear functions have to fulfill besides being nonlinear? Oh no.
Yes, yes. So I skipped a lot of nasty details because it's.
Okay.
No, but let me tell you because it's important. Thank you for the question. So this phi. So the only requirement that you have, actually there are refinements of this theorem where you can fix one of the two. I think you can fix the capital phi to a given form, which is given explicitly. So the only thing that you have to find are these small phi that are one-dimensional nonlinear functions. Again, they have to be strictly increasing, strictly monotonic, okay, of their arguments. However, I mean, this is where I'm putting if you want, the dust under the carpet. In general, determining these functions, if I give you a high-dimensional generic F, is a complex task because you have to determine a very complicated nonlinear function for all the possible values of its arguments. Even this is 1D, there are some precision issues that I don't want to go too much into the details, but at the end, the problem of determining this function is still NPR, if you want. So there is no way around the complexity of the initial problem. But still, I mean, this is, if you want, just a motivation to tell you that at least the representation exists, which is compact.
Okay, thank you very much.
Yes, there's another question.
Yeah, I really still don't get how come this function, we can like make any statements about these functions if k is actually a discrete variable, say spin up or spin down, if we're talking about a wave function. So I mean, I can't believe that for a generic function of n arguments, where all of them are continuous, let's say from real numbers, this holds. But what about the wave function, where all k's are discrete?
That's a special case of a real variable in a sense. So if you prove it for continuous real variables, then it holds also for discrete variables, right?
Yeah, but
I mean, you can always lift a discrete wave functions to a continuous one, just assuming that it's continuous in the middle.
Yeah, but okay.
So the only requirement
makes little sense.
So the only technical requirement is the function is continuous. So you don't need that.
Yeah, but I mean, this is, yeah, it kind of strange because phi only assume two values as it turns out, because so do k's, right? And that's why it's hard to tell, like you can take literally any function for phi, literally anything. For small phi.
No. So these are specific functions that correspond to the choice you put on the left. So if you want, there is a correspondence between what you put on the left and the phi's that you take here. So this is the main point. So for a given choice of psi, there is a choice of phi's. This is not a universal function, of course. So the function phi's depend on psi, yes, in a non-trivial way.
But how is that if phi's, small phi's, only assume two values? I mean, I can parameterize them by two numbers. So it kind of says that I can assign two numbers corresponding, depending on the left-hand side of this equation. Okay, this is not probably the question to be discussed now.
Okay, let's discuss about this later. But okay. Okay, so the other point that I wanted to make here is that sorry. So this kind of states represent volume law entanglement efficiently, so as shown in this paper. So the idea is very intuitive. So for example, if you consider a depth D neural network, so essentially, and you take typically these filters to be, you can even take these filters to be short range. So this is something that people do. So this by filters, I mean this matrix is W. Okay. So where are they? I lost them somewhere. Okay, so this so in the definition of the neural networks. Okay, so in the definition of the neural networks, you see that we have these matrices that act on my input variable. Okay, but you can take these matrices if you want to act only on a subset of the spins. So this is, if you want, a way to find again locality. And these kind of architectures are known as convolutional neural networks. So I'm just giving the name, and you can look them up. But essentially, the content of this theorem is that if you have D layers, so the depth of your network is of, even if you have short range filters and you have D layers, you can efficiently encode the volume law entanglement if if you want the depth of the network scales like the number of spins, or actually the linear size of your system. So if you are in 1D, this would be the square root of n. So let's say it would be n to some power of alpha, which will be let's again giving you the linear size of your system. So if you are in 2 dimensions, this means that in order to have volume laws of very long range correlations, if you want, you need to have a depth which is of the order of the square root of the number of spins in 2 dimensions, or the cubic root of the number of spins if you are in 3 dimensions, and so on and so forth. So you can mediate, if you want, these long range correlations working with deep networks that are not crazily deep, but they have a depth that scales typically with the number of spins. Okay. Now, in general, so there are representation theorems that hold more broadly. For example, when you try to connect these neural networks with tensor networks, which again is something you've seen during these lectures. So you've seen general parameterization of the wave function in terms of tensor networks. Then, I mean, what we showed recently actually is that again, in an attempt to somehow map, to chart this family of quantum states that parameterize physical quantum states. So these again are my physical, if you want, quantum states. So we want to understand, as I was mentioning, answering to one of your questions yesterday, in general, if you give me a Hamiltonian, I cannot tell you if exactly, I mean, at least in the most general case, if a given representation would be exact and efficient for that specific Hamiltonian. However, we can try to chart and try to understand how far a specific parameterization goes with respect to another parameterization. So to be specific, for example, there are gapped one-dimensional Hamiltonians. So the ground state of gapped one-dimensional Hamiltonians are a very special case because, as you know, as you've heard, I guess, this can be described exactly by matrix product state, which are this special class of tensor networks. Okay, so we know that gapped one Hamiltonians. If you know beforehand that the Hamiltonian is gapped, which is non-trivial to know. Then you know that there exists a ground state representation in terms of a matrix product state, okay, which is efficient. The bond dimension will be only polynomial in the sides of the system. Also, we know that in 2 dimensions this can be generalized, and there are PEPs, for example, that are a generalization of PEPs of matrix product states to 2 dimensions. So then, if you restrict yourself to only those PEPs that you can efficiently work with on a computer, so that you can, for example, contract and work with to approximate ground state energies or any other properties, then you can show that all the neural network quantum states essentially contain a broader class, if you want, of this family of variational states. So matrix product states, PEPs, gap-to-1D Hamiltonians also can be described efficiently in terms of these deep networks. And then there is some other regions, if you want here, of volume law states that essentially come from this statement that are not, if you want, efficiently described by PEPs or matrix product states, but that you can describe efficiently with deep networks. So again, this is an a posteriori motivation for this, for looking for alternative parameterization of the wave functions. And again, as has been shown in this paper, a posteriori you can somehow connect the two representations, showing that in a sense one is a special case of the other. Okay? Okay, so this is my first, my look at the representability issues, all the if you want what is related to what kind of states we can represent, which is a very interesting and open question, because as you can see, we don't know much about the rest of this space. Okay? So for example, we don't know where gapped 2D ground states are. So we don't know if we can represent them exactly in the 2 dimensions. This is still a very open question. So there is still a lot of unknown, uncharted territory here to try to understand and see how we can try to parameterize these states efficiently. So now let's finally go to the question that that was asked before. So essentially, what is the loss function and what is the learning? Okay? So learning in the quantum case. Now, so in the quantum case, for example, if we try to solve for the ground state of a given Hamiltonian, as I was mentioning yesterday, what we want to do is that we want to minimize the energy. Okay? So essentially, I can immediately define my loss function that will depend now on my parameters to be, if you want, the energy function, which is the expectation value of the Hamiltonian over a given parameterization of the wave function that in this case is given by the neural network. Okay, and as we've seen yesterday, we can write this loss function if you want. So this is the E of W in terms of an expectation value over this probability distribution P of K, this Born distribution of the local estimator of the Hamiltonian that in jargon is called the local energy. Okay? Or it should be called the local Hamiltonian, but it's called local energy, doesn't matter. It's the same thing. But I mean, again, this is what we saw yesterday. This, again, just to remind you briefly, the probability distribution P of K is given by this object here, and the local energy now is given by just the sum over K prime of the matrix elements of the Hamiltonian, okay, times, if you want, K prime psi over psi of K. So, and again, since at the beginning we were working, since from the beginning we are working with local Hamiltonians, K-local Hamiltonians. These matrix elements are only polynomially many. I can compute this local energy for an arbitrary K in polynomial time. Okay. Now, the main point. So this is my loss function, and as you can see, this takes exactly when I approximate if you want, this object with the samples. This takes exactly the form of the loss function that I discussed before, because you can write this as 1 over m, the sum of I that goes from 1 to m of the local energy computed over these samples. Okay, so you see that in this case, the role of the local loss, the per sample loss, as I called it before, is played by the local energy. So this is now my, if you want, per sample loss in the quantum case. Okay? You can also work out, for example, the gradient, the gradients of the energy. So, for example, you can work out the gradient of the energy with respect to an arbitrary parameter WP. And I'm not going to do the calculation explicitly. It's not very hard, but I will just write down the final result. You can show that this expectation value, this gradient can also be estimated as an expectation value over this probability distribution P. Okay? So if we write this now as, if you want, with this notation to indicate that I'm averaging over the distribution P. So this means a statistical expectation value over the distribution P. Then you can show that the gradient is written as the statistical expectation value over this distribution P of this local energy that will depend in general on K, times an operator that I'm going to introduce in a second that I call O. Okay. Minus, there is another term that comes essentially from the normalization, so which is again the mean of the local energy, times, okay, sorry, now I finished my space, so it's minus, so again, the statistical expectation value of the local energy, which is just the energy, by the way, times O star, so star means just the conjugate of this object. Okay, so you can just work this formula by the definition, and you will find that this is the what you get for the gradient of the energy, where I've defined this operator, if you want, OP. It's a diagonal operator in my computational basis, which is defined by the following. So it's just the gradient, the derivative, if you want, of the logarithm, actually, of my wave function amplitude with respect to the parameter P. Okay? So again, this is something that I can compute typically in an efficient way if I can compute also the amplitude of the logarithm of the amplitude with a neural network, for example, and also the gradient can be computed in a similar way. And then the strategy, it's clear. So what I do then, this is what the optimization algorithm is. So again, so at step 0, if you want, you initialize some random, if you don't know better, weights, W. Then at step 1, essentially, you sample from this P of K that will depend parametrically again on the choice of the right. So let's say that you are at step S of your optimization. So this is your probability distribution will depend on the current set of variational parameters, WS. So then you generate a lot of these K1 up to Km samples. Okay. Then you measure, if you want, both the local energy and the gradient of the energy. So you obtain estimates of EW, okay, again as a statistical average of the local energy, and of the gradient of EW as the expectation value that the difference of two expectation values that I wrote up. So I'm not going to write them explicitly again. Then with this information, so both with the energy and also with the gradient, what you do is that you do the gradient descent, as I was telling you before. So at step S+1, your parameters now will be just the old one minus some learning rate, and then use this the derivative of the energy with respect to parameter P to update with this stochastic estimate of the gradient your parameters. So, and again, you are doing stochastic gradient descent, and in the limit in which you are doing this operation, a lot of times you will converge I mean, to the global minimum of, in theory, of this loss function. So you will find the best, if you want, variational state that has the minimum energy compatible with the Hamiltonian that you've given. Okay, so this is in a nutshell how this algorithm works, and you can see also the connection with what people do in machine learning. Okay, so a question that maybe I haven't answered yet is how do we compute these gradients? So you see that here the thing that I swept a little bit under the carpet is how can I compute efficiently, if you want, this OP? So how can I estimate the gradients of the log of the wave function efficiently if I have a parameterization of the wave function in terms, for example, of a neural network? Okay. So I will not give you the full details because it's a bit technical, but I just want to give you a quick idea because this is a key concept also in machine learning. So, and this is the concept of how can we compute gradients.
First
Yes.
question by Anton.
Okay, yeah, thanks. I'd like to ask probably again about the convergence issue related to the gradient descent method. I mean, there's, as always, as far as I know, it's a pretty complicated problem to ensure a stable convergence to a reliable minimum as opposed to some random local minimum. And as far as I know, people from machine learning have invented a lot of ways to overcome this. And my practical question relates to, out of it, what is actually well tested and works in the field of quantum problems? What tests, at least at the empirical level, work to ensure convergence to a proper minimum, maybe some relaxation schemes, and I don't know,
Okay, so
some
let
protocols.
Yes, so in practice, as I was telling you at the beginning, one of the conditions you need to impose to converge to the global minimum is that the learning rate goes to 0, okay? Because you want to lower the temperature. So this is equivalent to somehow to performing simulated annealing. So you have this temperature and you want to lower it. So all the most efficient, if you want, empirical of what people use in the field are approaches that in a way or another reduce automatically this learning rate whenever you run these iterations. So there are different ways of doing that. One very popular way is called ADA max, ADA delta. I mean, there are different variants, but these are all based in a way on the idea that you can automatically find a small, reduce this eta as you approach the minimum. So this is a very, it is a very long discussion that maybe we should have offline because it's a very, you know, it's a broad field on optimization.
Yeah, and could you please then give just a few word comment about whether all those rules of decreasing the learning rate are vulnerable to the fact that actually we sample some stochastic quantity, it contains fluctuations, so that in the end of the day it's available with a finite, not very large precision. Is this a big problem?
So this analysis that I showed you, very simple-minded, that is based on the Langevin dynamics, which is not 100% exact, but can be refined by, it has been refined by mathematicians. It contains intrinsically fluctuations. So this is all based on fluctuations. So okay, you are converging to the ground state because you have fluctuations. Yeah. So it's actually the fluctuation.
No, I mean, in our case, it's like I meant not the fluctuations from the gradient descent rule, but those from the fact that we actually estimating the energy itself. So in some sense, the loss function itself is only available up to some finite precision.
No, but this is precisely my point here. Also, the loss function in standard applications is not known exactly. It's known through samples. Okay.
Okay.
So this is the main point, that the loss function is never known exactly. It's always known approximately. Yeah. And also it's gradient.
Okay.
So just to give you now a very quick, Marcus, how long do you have? 10 minutes? Or?
Yes, 10 minutes.
Okay, more or less. So, but just let me give you a very quick overview of how we do this in practice. So this is this topic of automatic differentiation, that it's important that you will see it also during Filippo's presentation. So there are two different ways of doing automatic differentiation. I won't cover them. So one is called forward mode, the other one is called backward mode. So again, because my goal is to compute efficiently and automatically, so I don't want to write analytic gradients of complicated nonlinear composition of nonlinear functions, because that's going to be a nightmare if I want to change something, for example, in my architecture. But I want something that computes this automatically. And forward mode is a way of performing these gradients automatically, which is very efficient when I have a function from Rn to Rm. And this is mostly efficient when m is much smaller than n, the input. Okay? In the other case, backward mode, which is mostly used actually in machine learning, is more efficient when in the other limit. So typically when you have a smaller number of outputs, let's say 1 or 2, m is equal to 1 or 2, and the number of inputs is very large. Okay? However, backward mode is a bit more involved, and I don't want to discuss it today, but I want to discuss briefly forward mode because it's easier to understand. And it's nicer because it's based on this idea of the dual numbers or dual algebra. So, and the idea is that when you have a variable x, for example, you want to take gradients with respect to this variable x of arbitrary function, you can augment this variable with a dual. So you introduce a variable, so a dual variable to this x, which is called x prime, and it is coupled to a symbol that is called epsilon. So what are the properties? So essentially in this representation, both x and x prime now are real numbers. Okay. And epsilon is a symbol that was defined by Clifford, a mathematician, which is nilpotent. Okay, so nilpotent means that the square of this symbol is by definition equal to 0. Okay, so another very famous symbol that has been defined by mathematicians.
Isn't this something related to Grassmann algebra? I guess.
Yes, it is related. Maybe we can discuss later. So
okay, again, yeah.
Yeah, if we can keep your question for the end of the lecture because we are running a bit late.
Yeah, I totally understand that. Let's postpone it. It's kind of a long discussion as far as I understand.
So, but just wanted to mention that these kind of dual representations are very famous and important in mathematics in general. For example, with complex numbers, you introduce a number which has this property I squared is equal to -1. So here we introduce a nilpotent symbol that is related to Grassmann algebra. And the reason why you want to do that is because then you can define a completely closed set of algebra under these dual numbers. For example, when you add the two numbers, so let's say this is my first dual number with another dual number, okay? Then you see that if you want the principal part, I don't know how they're called. So let's say the first component adds normally, and also the second component adds like this. Okay, but more interestingly, when you do, for example, a product of two dual numbers, okay, so you see that the first component is just the product of the principal components, let's say, of these two dual numbers. But then, due to the fact that epsilon square is gives 0, there's only this one term that survives. Okay? because the term that is epsilon square, if you want x prime, y prime, is exactly equal to 0. So you see that if you use this algebra, essentially what you get here in this expression is always related to the derivative of the function that you are taking. So and this is the main idea that is used in automatic differentiation. That you, instead of working with real numbers, so whenever you do a mathematical operation, an algebraic operation on your computer, you change these operations from regular numbers to these dual numbers that carry this epsilon part, if you want. For example, if you have an arbitrary function, you can define that is analytic. You can define if you want the result of the application of this onto a dual number to be equal to f of x plus epsilon f prime of x. Okay. So in general, then if you want the derivative of x, you would compute this f on epsilon 1. So you would set x prime equal to 1, which is called the seed of this automatic differentiation, and this would give you a pair of dual numbers where the first, real numbers, where a dual number where the first component contains f of x and the second one contains the derivative. Okay. You can generalize these to composite functions, but in general, the idea is that working with compositions also of nonlinear functions, it's very straightforward now. You just need to replace your input variables with this augmented algebra of complex or of dual numbers. Okay.
Mm-hmm. Okay. Okay. Sounds quite familiar. Yeah. Thanks.
Great. Now, in the last 5 minutes, I will discuss actually something which is relevant because it goes beyond the problem of finding the ground state. So, and the question that I want to answer is, can we learn, if you want, more than ground states? Okay. So can we find, if you want, an approximation, or can we find a learning principle that goes beyond the static variational principle to solve, for example, approximately? So the problem now is to solve in a variational way, where variational has to be defined, the time-dependent, for example, Schrödinger equation. So I want to solve, the Schrödinger equation for a given state phi with some given Hamiltonian that in general can be time-dependent. Okay? So I want to find, if you want, a representation of phi of t in terms of some parametrized wave function psi that will depend in general on some parameters w. Okay. So the question is, how can I find this w, if you want, in general for each time t? Okay. So this is if you want, a generalization of the static gravitational principle, because here, as you can see, I don't have any energy to minimize, but I still want, the question is still well defined. So, and how can I try to represent this state at each time in the form of a variational state whose parameters now in general will depend on time? Okay. And this is what is solved through the so-called time-dependent variational principles. And the one that I'm going to use today is the one by Dirac and Frenkel. There are other incarnations of this variational principle, but I won't discuss them. So sticking to this specific representation, also explained in modern terms. So this time-dependent variational principle can be interpreted in a very nice geometrical way, actually. So the idea is that at each time t, you have a state or a vector in your Hilbert or vector space phi of t. Okay. And what happens is that this vector is rotated because the unitary, because the Schrödinger equation induces a unitary evolution, as you know, into, if you want, an exact state that we can call phi of t plus delta t. Okay, so I'm considering an infinitesimal evolution of a step delta t. On the other hand, I can think that I have a variational state. Okay, so here I'm assuming that at step t, it's already true that my variational state is equal to psi of w of t. So some choice of the parameters. Okay, so the question is what happens at time t plus delta t? Because if I can solve this problem at each instant of time, because of the Schrödinger equation is a first order linear equation, then I can first order differential equation, then I can solve this for all times. So if I assume for a moment that at time t, my initial state is already given by the exact time evolution, the variational state is already coincident with the variational evolution, what does it happen in a time step? So it happens that the exact time evolution will rotate this state to this phi, and it will happen that in general, my variational state will go into something which is essentially psi of w of t plus delta t. So you can imagine that the variational parameters in your representation have changed also. They have a time dependence, and they go to a value which is w of t plus delta t. Okay, so this is the idea. Then the idea of the variational principle is to minimize the distance between the exact state, the exactly evolved infinitesimal state, and the approximately evolved state. And this distance will be a function not of the variational parameters, but of the variational parameters derivatives. So this is the complication, if you want, with respect to the static ground state principle, variational principle, because now the thing that we have to minimize does not depend on the variational parameter itself directly, but it depends on the derivatives of the variational parameters. This is best seen because if you write these two states, so the state A, so to speak, as the identity operator, so we linearize the Schrödinger equation applied on my initial state T, and my state B, which is my variational state, as 1 plus delta T. So you can show that when you linearize, you can write it like this, actually, where these OP are the operators that I defined before. Okay, so you have these two states. Now, again, WP are the time derivatives of my variational parameters, and OP are the operators, the derivative of the log of the wave function. I'm not proving this equation, but it's straightforward if you think a little bit about it. And then what you do is that your loss function now will be a loss function that depends on this WP, so the time derivatives of the variational parameters. And it's the overlap, if you want, between these two states A and B. Okay. So since B depends parametrically on WP dot, you see that also the loss function will depend on WP dot. So I can optimize, try to, in this case, maximize, but this is just the same, this loss, so this overlap, in order to have B to be as close as possible to A. Okay? So this is the idea of this variational principle. So if you do this maximization analytically, actually in this case you can do it analytically because it's a quadratic optimization problem, you will find that essentially this W dot, so the time derivatives of the variational parameters, have to satisfy the following equation of motion. So I will write it down and then I will comment. You can see that it's a bit similar to what we saw before. But so you see that we have defined so a matrix as P and P prime, which is actually which is defined as the so it's derivative of the wave function with respect to parameter P. The overlap with the wave function, the derivative of psi with respect to P prime. Okay, and this can be estimated. You can show it as the expectation value again on this Born distribution of O star P or P prime minus so it's an emission matrix, which is very important, and it's related to the geometry of this variation on the space. This is known as quantum geometric tensor often. And essentially, it's the metric of the variational space. I'm not going to give you the details of why this is the case, but it essentially fixes the metric. So how far are two states is quantified by the overlap, and this is the metric associated with the overlap, essentially. Okay, and then on the right hand side, you see that these other quantities are things that we can measure, or if you want, we can compute efficiently, again, as expectation values over the Born distribution. So all of this can be, again, estimated. So both this matrix S and these expectation values can be estimated from samples from my distribution, P. So this algorithm, which is known as the time-dependent variational Monte Carlo, I mean, which is discussed somehow in this paper. Is a generalization of the static time-dependent of the static Monte Carlo, in the sense that you still have the same steps. The only difference is that at each, instead of having an optimization, you now have a time t. So instead of having an index k, s, sorry, that was the step index, you now have that that your Born distribution will depend on time, and it will be given by this object, essentially. So at time t, you have a certain set of variational parameters, W of t. So the first thing that you do is that you sample from this W of t. Then you measure, as we did for the ground state, right? Using these samples S of P prime, so this matrix, and also, if you want, this term here on the left that we can call F of P. Stochastically, again, this will be subjected to noise. And then you solve a linear system of equation to find the WP. So again, as you see, you can write this equation of motion. That's something like so S. So this matrix S applied on WP, you see, as you can see here, is equal to minus I F, where F is a vector. Okay, so sorry, S is a matrix and F is a vector. So what you can do is that you can solve this linear system, and you will find your W dot. So essentially your best time derivatives. And then at step 4, you can use this information, so these derivatives, essentially to go to the next time step. So now, I mean, the easiest but not the most intelligent thing you can do is to use these gradients with a simple Euler, for example, integrator. So this is just a first order integration for these differential equations. You can also use, in this case, the previous, if you want, information on the derivatives that you know, or you can use a Runge-Kutta or higher order schemes. And this will allow you typically to also, if you want, integrate the equation of motion, and you will have the full trajectory, if you want, for these variational parameters from time t equals 0 to time capital T, let's say, which will be your last time you're interested in. Okay. Okay, so I think this is a good point to stop. Filippo will discuss a generalization of this also for imaginary time. That's what we use for optimization, but I don't have time to discuss it today. Again, so if you have a few questions, maybe I can take them if Marcus agrees. Otherwise, we can reconvene at some other time.
Okay, so thanks first of all for your two very nice lectures, and of course, if there's a question, we will take them. So there's one in the chat. Since the neural net quantum states includes MPS, I suppose it will be possible to directly compare the efficiency and accuracy of this method and DMRG. Could you comment on this? Which one performs better or how much?
Yes, so so again, for one-dimensional systems, metrics for the states are extremely efficient. So essentially, it's the most efficient thing you can do for one-dimensional lattice systems. So typically, you know, the computational time required by an NQS to obtain similar accuracy is larger. But if you compare it to for example, in terms of, there are some even one-dimensional systems that are harder for MPS, for example, if you have periodic boundaries. So in that case, you can find if your system is large enough that NQS already gives you some, if you want, speed advantage over MPS. But again, in 1D, if you know that your Hamiltonian is gapped, you should definitely use an MPS because that's typically more efficient. The question is if you want to do dynamics or if you want to do two dimensions, then in that case, then NQS is a bit more general.
Okay.
So there are
this point,
you can see these comparisons in papers. If you want, I can give you results.
Okay, at this point, I would apply a slightly modified time-dependent variational principle and maybe stop the discussion here, but feel free maybe to ask your question on Slack, and Giuseppe can from time to time look at it and answer there for all of them. Because
yes,
that we don't run too late today because we have post the session early starting. So I would suggest a 10-minute break and start with the second lecture of David.